Our next speaker is Patrick Mehlitz. He's from Brandenburg University of Technology. So for today, his topic is asymptotic regularity in non-smooth mathematical programming. So the floor is yours, Patrick.
Yeah, thank you very much for the introduction. Good evening and good morning to everybody, depending on where you're sitting. Yeah, I want to speak about asymptotic regularity in non-smooth programming, which is somehow connected to the talk of Gabriel we saw yesterday morning, where also asymptotic optimality and regularity conditions were discussed in some context. And I wanted to check whether these concepts can be somehow generalized to settings of non-smooth optimization. And here I will focus on connection to the limiting tools of variational analysis by Boris, because I came up with the idea that tools of sequential regularity and sequential stationarity should be, in some sense, compatible with sequential tools of variational analysis. So that's the basic idea behind the talk. I will give a short introduction first and speak about some preliminaries from variational analysis, although I think that most of you are familiar with that. And then I will speak about asymptotic stationarity, which is the basis of asymptotic regularity, the concept of interest, and I will conclude with some applications of the stuff. Good. And the problem we want to discuss here is a standard optimization problem. Phi is a scalar objective, assumed to be locally Lipschitzian, and the feasible set is modeled as the set of all zeros of a set valued map, which is assumed to have a closed graph. This model is very general. It covers, for example, standard nonlinear programs, but also programs with geometric or set constraints, meaning that g of x is in some set k and k is closed. Also possible is the setting of equilibrium problems, for example, where phi models the solution set of variational or quasi-variational inequalities. So all these problem structures are summarized in the model P. And let's review some stationarity concepts for this program, which can be found in the literature. So therefore, we use the tools of limiting variation analysis, meaning the limiting normal cone, limiting subdifferential, and limiting coderivative. Okay, so a point x bar feasible with this program is called M stationary if we can solve the generalized equation you can see there, so that 0 is an element of the limiting subdifferential of phi at x bar plus the coderivative of phi at x bar 0 for some multiplier lambda. Now it's possible to generalize this concept a little bit when introducing a leading multiplier in front of the subdifferential of the objective, some lambda 0. And this looks then a little bit like Fritz-Jones conditions from nonlinear programming, which is why someone might be tempted to call that new stationarity condition you can see now as Fritz-Jones Mordukowicz stationarity. I will speak of FJM stationarity for brevity. And what we postulate here is that the additional multiplier is non-negative and that the tuple lambda 0 and lambda is not trivial. That means it not vanish, because otherwise the condition would be trivial. And what we see is, obviously, every M stationary point is FJM stationary, choosing lambda 0 equal to 1. And if we have an FJM stationary solution where lambda 0 is positive, then we can rescale the equation, dividing it by lambda 0, using positive homogeneity of the coderivative in order to get M stationarity. Both of these stationarity concepts can be used as stationarity conditions, or as necessary optimality conditions for the program P in some context. So let's fix a local minimizer of P. Then we know without any constraint qualification that this point must be FJM stationary. And in order to infer from that this point is M stationary, we somehow need to ensure that the kernel of the coderivative reduces to 0, which is nothing else but metric regularity of phi. Okay, I called this weak statement because one can get something much stronger when postulating that phi is metrically subregular at x bar 0. Then we already know that x bar is M stationary without going the complicated way to FJM stationary first and from that to M stationary. So the direct path is the better one. And we can even strengthen the second statement using the tools of limiting directional variational analysis, but I don't want to speak about this here. The basic question in this talk here is the following. Is there a stationarity concept for P with the following properties? First of all, it should hold for each local minimizer, even in the absence of constraint qualifications. And afterwards, and additionally, we want to construct it in such a way that it is more restrictive than FJM stationarity, but less restrictive than M stationarity. And if we have such a concept, then we are interested in the question, what does it need in order to come from this new stationarity concept to M stationarity? And this regularity concept is then hopefully less restrictive than metric regularity, which then would be a good thing, because then we have a new constraint qualification in non-smooth programming guaranteeing M stationarity of local minimizers. So that's the plan. And here is the figure I'm dreaming of in some sense. So the black boxes and black words there are the known things. The black arrows are the known relations. And the red things are the things we're going to construct here. So we construct something called AM regularity, which is necessary optimality condition in the absence of constraint qualifications, and with the aid of AM regularity, we can infer M stationarity of the local minimizer of interest. So that's the plan. So some preliminaries, I will go through that very fast, because I think everyone knows this. So we are basing on the limiting variational object of the limiting or Mordukhovich normal cone, which is the outer limit of the regular normal cone. And I think all of you are familiar with the robustness of this variational concept, yeah, because you can take also the outer limit of the limiting normal cone at a certain point of a set, and that recovers again only the limiting normal cone. That's a quite fine observation. And using this limiting normal cone, one can introduce numerous tools of generalized differentiation. For example, the limiting subdifferential, which is based on the limiting normal cone with the epigraph of the underlying function, and also the limiting co-derivative, which is based on the limiting normal cone with the graph of the set-valued map. And I will utilize some notions of Lipschitz continuity of set-valued mappings. I think this is also familiar to everyone, but let's recall the basic concepts. So we speak of metric regularity at a certain point of the graph of the set-valued map if we find neighborhoods U and V of X bar and Y bar and some constant kappa, such that this error bound property you see there holds, which means we can estimate the distance from X to the pre-image from above by kappa times the distance of the Y to some image set. And this gamma to the -1 is the inverse mapping associated with gamma. When we fix Y to Y bar in this definition, then we come up with the notion of metric subregularity. And another important property is the Aubin property or Lipschitz likeness of gamma at a certain point. There we need a slightly different Lipschitz estimate to hold for the set-valued map. You see it on the bottom of the slide. Yeah, don't go into the details. I think you know this. Something also well known is this Mordukhovich criterion. We know that the set-valued map gamma, locally closed around X bar Y bar, possesses the Aubin property there if the co-derivative at 0 only contains 0. And we also know that gamma is metrically regular at X bar Y bar if the inverse is has the Aubin property at Y bar X bar, which means that the kernel of the co-derivative reduces to 0. As I said, these criteria are called Mordukhovich criterion. And in the literature, we can find several much weaker conditions engendering metric subregularity. Obviously, the Mordukhovich criterion is sufficient for metric subregularity, but it's often much too restrictive, which is why, for example, Querer's first or second order sufficient condition for metric subregularity appeared, which are much less restrictive than metric regularity. Okay, so that's for the preliminaries, and now we can start with the stuff I actually want to tell you. So I will start with the stationarity concept of interest we are analyzing here. So we fix a feasible point of the program P, and now the idea is that this point should be almost stationary in some sense if we find a sequence of, let's say, epsilon stationary points converging to the point of interest. And that is precisely what this definition says. So we call a point asymptotically Mordkovich stationary, or AM stationary for short, whenever we find a sequence xk, yk in the graph, some sequence epsilon k, and some sequence lambda k, such that xk goes to x bar, yk goes to 0, epsilon k also goes to 0, and such that this epsilon stationarity condition at xk, yk can be guaranteed. And I want to point your attention to the fact that the sequence lambda k is not assumed to be convergent to something. Actually, it's not even assumed to be bounded, because if lambda k is bounded, then we can extract a subsequence, take the limit in this inclusion, and we can directly come up with M stationarity, and thus, for example, FJM stationarity with leading multiplier 1. If lambda k is not bounded, then we can rescale this generalized equation there by dividing it by the norm of lambda k, and again we take the limit along a subsequence and come up with FJM stationarity with leading multiplier lambda 0 equal to 0. So this concept there is more restrictive than FJM stationarity, and obviously each M stationary point is also asymptotically Mordkovich stationary, but not necessarily vice versa. Now the first theorem, which is important, can be shown based on the stationarity concept. We know that each local minimizer is actually AM stationary. And how this can be proven? Not that difficult. We only have to consider a suitable penalized version of the program of interest. So we allow some perturbation of the feasible set. The original feasibility condition was 0 in capital phi of x. Now we just say that y is an element of phi of x. So we perturb the 0 a little bit, and we restrict ourselves to a closed ball around x bar 0 for x and y, and we induce some penalty terms in the objective. And one can show that the sequence of global minimizers associated with this program can be used to construct the sequences appearing in the definition of AM stationarity. So we know each local minimizer is actually AM stationary. So fine. Now the question arises, what do we need in order to come up with M stationarity from that? And that is what asymptotic regularity does. In order to define this stationarity, this regularity concept, I introduce a set value map M, mapping from Rn times Rm to Rn, which basically collects all the images of the co-derivative at a given point x and y. So that is what M does. And with this definition of M, we can observe the following things. First of all, if we think about what is M of x bar 0, this is precisely the image of the co-derivative at x bar 0, which means that x bar is M stationary if and only if the intersection of the subdifferential and minus M of x bar 0 is non-empty. One can also show that if x bar is AM stationary, then the intersection of the subdifferential and the outer limit of the the images of M, x, y, if x goes to x bar and y goes to 0, if this intersection is non-empty. Okay, we know that this limit superior, which appears there, the set limit, could be is always a superset of M of x bar 0. So this again recovers that AM stationarity is less restrictive than M stationarity. And another observation is, I should mention that this condition in the middle of the slide is not sufficient for AM stationarity. In order to get that, we need to additionally impose continuous differentiability of phi. Okay, but that's only a remark. the basic observation is, in order to come from AM stationarity to M stationarity, we need to ensure that this limit superior, which appears here, is included into this set M of x bar 0. That's all we need. And that is precisely the definition of asymptotic Markovitch regularity, or AM regularity for short. So we just postulate that the set value at M is outer semi-continuous at x bar 0. That's all. And based on the observations on the page before and the fact that each local minimizer is AM stationary, we then know that if we have an AM regular local minimizer of P, then this point must be M stationary. Okay. Now the question arises, yeah, this is a good definition, but how is it related to all the other notions of CQs which apply to this program P? Are there any? And yes, there are. The first observation is that if phi is metrically regular, I think this is the standard assumption in order to get M stationarity, or it was some years ago. That means if the kernel of the coderivative reaches to 0, then we know that this x bar point is also AM regular. So metric regularity is sufficient for AM regularity. Another thing which is sufficient for AM regularity is polyhedrality of phi, which means if the graph of phi is the union of finitely many convex polyhedral sets, then we know that each feasible point of the program P is AM regular. Now comes the interesting question, what about the relation to metric subregularity? And here it gets a little bit tricky, because we can show that neither AM regularity is sufficient for metric subregularity nor vice versa. So these properties are not related at all. I have brought two examples here. The first one is constructed in such a way that these images of the coderivative are always subsets of R plus, and M of x bar 0 is also R plus, which means that this here is an example where the point x bar equal to 0 is AM regular. But due to the appearing square function here in the second case of phi, we can easily show that this mapping is not metrically subregular at the origin, which means AM regularity is not sufficient for metric subregularity. On the other hand, this simple example here shows again some quadratic terms appear that we can have metric subregularity. This here, for example, can be easily checked with Ferrer's second order sufficient for metric subregularity. A little calculus is necessary, but not that much. And on the other hand, we can see that AM regularity fails in this context. So both properties are not related to each other, but they have something in common. Both of these properties guarantee validity of the pre-image rule, which is more or less all we need in order to infer M stationarity for this abstract program. What do I mean with pre-image rule? Yeah, what does the theorem here say? So we fixed a feasible point x bar of P, which is AM regular, and we define the feasible set of P just as M. Then we know that AM regularity ensures that the limiting normal cone to the feasible set can be approximated from above by this image of the coderivative at x bar 0, which is precisely a term, this term is stated in terms of initial problem data, which motivates to call this relation a pre-image rule. The same pre-image rule we get under validity of metric subregularity, but we get maybe something stronger if we know the precise modulus of metric subregularity, which was the infemal kappa appearing in the definition of metric subregularity. So if we know that, we can get an additional bound in this pre-image rule, but in general, we get the same if we do not know the modulus. And here are the relationships of all the properties I mentioned. So metric subregularity and AM regularity both imply the pre-image rule, but are not related, and both of them are implied by metric regularity and polyhedrality of phi. Okay. Finally, I'd like to talk about some applications of AM regularity, or some consequences. Consequences would be a better word here. The first thing I would like to discuss is the setting where we have decoupled constraints. What does this mean? So we assume that phi is given in some product structure, meaning that we have a first component, gamma of x, which is again a set mapping with closed graph. And the second component is just x minus c, where c is closed, which means that all feasible points of P just have to belong to the constraint set C. And we want to decouple this constraint set C in some sense. What does this mean? Okay. Formally, if we apply the concept of AM regularity to this map phi, we impose some product rule from co-derivative calculus and get that the mapping M, which is involved in the definition there, takes the form you see in the middle of the page. And what happens is x is fixed. You perturb the point in the graph of gamma here with this y1, and individually you perturb also the x here in C. So x minus y2 has to belong to C, which means that the point x on its own does not necessarily need to belong to C in this perturbation here. However, it would be fine due to some algorithmic applications we have in mind. Again, this comes from the, let's say, from the concept of asymptotic regularity used, for example, for nonlinear programs, and there these constraint qualifications are interesting in the context of augmented Lagrangian methods, for example, primal dual methods in general. And there it would be fine if the iterates already belong to the abstract constraint set C. So what I wanted to say is, it would be fine if we can state a constraint qualification in terms of the mapping M tilde at the bottom of this page here, where we do not perturb x, so that x belongs to C a priori. And now the question arises, is it possible to state a constraint qualification in terms of M tilde and not in terms of M, and still infer M stationarity of the program P, where phi is given as in equation number 1. And indeed, this is possible if gamma is, in some sense, stable enough. And stable enough means here that this gamma has to possess the Aubin property at x bar 0. So what does the result say? If we have a local minimizer of P, where phi is of the product structure of interest, and if we know that gamma has the Aubin property at x bar 0, and if the milder constraint qualification in terms of M tilde, saying that M tilde has to be outer semi-continuous at x bar 0 holds, then we know that x bar is M stationary, which means this generalized equation there possesses a solution lambda. Yeah, due to the fact that we use decoupled constraints here, we refer to this constraint qualification 2 as decoupled AM regularity. If gamma does not possess the Aubin property, this is not in general a constraint qualification for the program P, so we have to be careful here. And even in situations where gamma actually possesses the Aubin property, decoupled AM regularity could be strictly weaker than AM regularity. So in this context where gamma possesses the Aubin property, one should always rely on decoupled AM regularity as a constraint qualification and not on AM regularity. Now we can specify this for the setting of geometric constraints. So we fix gamma to be just the mapping g of x minus k, where g of x is single valued and continuously differentiable map. Actually, G locally Lipschitz continuous is enough, but for brevity of notation, I just refer here to continuous differentiability, and K is just a closed set. Then gamma more or less is just a Lipschitzian perturbation of the set K, which means we have the Aubin property here everywhere. So we can apply decoupled AM regularity as the CQ of interest, and the map M tilde takes the form you see there. So we have the derivative of G transposed times the normal cone to K. We perturb the normal cone to K from G of X away. And we have the normal cone to C, but at X and no perturbation there. And the outer semi-continuity of this map at x bar 0 is weaker than the metric regularity of the associate mapping phi, which reads as the so-called generalized MFCQ or no non-zero abnormal multiplier constraint qualification, which you can see there. So this is in generally more restrictive than decoupled AM regularity. Now I want to speak about a very particular case of geometric constraints, namely so-called disjunctive constraints, where the K is replaced by some set D, which is the union of finitely many convex polyhedral sets. And we assume that C is the overall Rn here. This model is also quite fine because it still covers numerous interesting structured optimization problems as NLPs, mathematical programs with complementarity, with vanishing, with switching, with cardinality constraints, with probabilistic constraints in some sense. So again, this is a quite interesting model. And if we apply here the concept of AM regularity, the map M looks as on the page before, as you can see there. So we have the derivative of G transposed times the perturbed normal cone to D. But we can get something better, because the disjunctive structure of the set D allows us to simplify the mapping K whose outer semi-continuity we actually have to consider for regularity. And that is content of the theorem there. So if we have a feasible point of the disjunctive program, and we consider the map K, which just is the derivative of G at X transposed, evaluated for the normal cone to D at the fixed instance G of X bar. So we do not perturb the input of the normal cone at all. The normal cone is stable. Then we only have to consider outer semi-continuity of this map K at X bar, and that is precisely equivalent to AM regularity in the setting. So we only have to perturb the point which models the derivative. And that is quite fine, because this result shows that AM regularity is precisely the cone continuity property, also named AKKT regularity, of Roberto Andriani and his working group when applied to NLPs. And similarly, we recover similar AKKT regularity properties, which have been published for MPCCs, for example. Another point is that we can see from this relationship that AM regularity is independent of generalized versions of Abadi's CQ, Grignard's CQ, and pseudo as well as quasi-normality. So this constraint qualification is, yeah, in some sense, a little bit separate from the other ones. And the final application I'd like to speak about is variational calculus. We can apply decoupled AM regularity to the constraint system X is in K and X is in C, which models the intersection of K and C. And then from our theory from before, we know that if the sum of the normal cones to K and C, this perturbed sum, is outer semi-continuous at X bar, then we get the intersection rule for limiting normals. Okay, this is a new approach to the intersection rule. Let me mention that this, one might be tempted to call it variational stability condition appearing in the theorem, is equivalent to saying that if we take the outer limit of the sum of perturbed regular normal cones, that this is a subset of the sum of the limiting normal cones appearing here. This is a simple diagonal sequence argument. Then we can prove, for example, the intersection rule for limiting normals directly from the fuzzy intersection rule for regular normals, because we know that the perturbed sum of regular normals is stable. Another point I'd like to mention is that in the standard literature, the intersection rule for limiting normals is guaranteed via normal constraint qualification, which means this intersection of normal cone to K and to minus C is just 0. And sorry for that. And this condition corresponds to metric regularity of the map, which assigns to X, X minus K times X minus C. And this is much more restrictive than the variational stability condition. And from the intersection rule for the limiting normals, we can infer A lot of other calculus rules for limiting normals, but also, for example, for the co-derivative. And indeed, one can formulate new sufficient criteria for validity of the sum or the chain rule from co-derivative calculus using other variational stability conditions. Okay, that were some aspects on this asymptotic regularity I wanted to mention. Yeah, some open problems. There are a lot. First of all, it has to be studied whether there are some valuable, let's say, sufficient conditions for AM regularity, because until now the only conditions which are quite fine for that are metric regularity and polyhedrality, but both are in general too strong. Maybe there is something else which is sufficient but weaker than the metric regularity. Sorry, one can easily check, for example, that first and second order sufficient condition for metric subregularity are not sufficient for AM regularity. That can be easily seen by examples. So I also mentioned that this sequential CQs turned out to be valuable in the convergence analysis of mathematical algorithms, primal dual algorithms. So the question arises whether this theory on asymptotic regularity can be used successfully and applied to convergence analysis for algorithms from non-smooth programming. And the third question is if there is a reasonable concept of directional AM regularity, because it turned out that using directional limiting calculus, we can provide a refined analysis, for example, for metric subregularity, and get new and fine conditions for validity of metric subregularity. And the question arises, is this possible in this new setting as well? Okay, that was everything I wanted to tell you. Thank you very much for your attention.
Thank you very much, Patrick. It was a very interesting talk. So we are running out of time, so maybe we have time for just one quick question or a comment for Patrick.
Can I ask? Oh, sorry. No, please go ahead.
Sorry, there was someone apart from me.
Go ahead, Alex. You are first.
Oh, am I? Okay. Thank you very much, Patrick, for your presentation. We already had some discussions around these things by correspondence. Finally, it is possible to actually attach the name to the face, and this is one of the positive outcomes of our workshop. This is already a good thing. So I like you trying to actually find what is essential in the conditions which we are using. You are replacing strong conditions like metric regularity by weaker conditions, subregularity, which is natural. I still have a feeling that something is missing a little bit in your definitions. You are claiming that this asymptotic definition is different from subregularity and incomparable. In fact, your talk was supposed to prove this, but I have a feeling that your definition needs a little bit of fine-tuning, and then the connection should become obvious. And during your presentation, I saw a few moments where I would do things a little bit differently. Definitely, we don't have time now for a detailed discussion of these things, but my feeling remains the same, that it can be fine-tuned. And my suggestion to you to look more carefully, for instance, you are taking limits of limiting objects. Why not combining these two limiting processes into one and to work instead of limiting objects with the original Fréchet objects? Maybe you will find a way to get rid of unneeded limits. But this is just a hint. I promise to keep my comment short. Sorry, Vanessa, I'm finishing here. Thank you again, Patrick, for your presentation.
Yeah, thanks for your comment. And yeah, you are right. There are some possibilities to work with Fréchet concepts, but there are some problems which also have to be taken into account when doing this. But maybe the overall, as you said, maybe the overall concept has to be fine-tuned from the beginning in order to get something stronger. I think the essential problem with this approach here is that in contrast to metric subregularity, we come here always from the optimization context, because AM regularity is only reasonable in the context of AM stationarity. As a stability property for self-valued maps, AM regularity alone is obviously reasonable, but we can prove things only via the stationarity concept, which is underlying, which is a little different. So, yeah,
but stationarity can also change.
Yeah, we should stay
while this slide is on the screen, 30 seconds more. In this last formula, you have xk in the first term and xk in the second term.
Mm-hmm.
I suspect that this should be different xk's, and this can change a picture a little bit, or maybe clarify the picture. Just a hint. Sorry, Vanessa, back to you.
Bruno, would you like to go ahead with your question very quickly?
Okay, very quickly then. So the original sequential optimality conditions by the Brazilian researchers, I think they always had some kind of algorithm in mind, like augmented Lagrangian or something like that. So do you also have some kind of algorithm in mind? Say something canonical that not canonical, but yeah, something natural for the kind of setting you are considering.
Yeah, something natural would be some kind of augmented Lagrangian method if you take geometric constraints, for example. But in the more general setting, I'm not aware of a concept which is suitable to work with this constraint qualification. But yeah, the more specific case of geometric constraints precisely would induce or make it possible to apply augmented Lagrangian, and in this case, this asymptotic state regularity condition would work perfectly fine.
Oh, okay. Thank you. I have more questions, but I'll ask later by Slack or something like that. Okay,
yes, please. Let's move our discussion to